if we look at it, the decomposition will give us the calcium oxide in solid state and the carbon dioxide in gaseous state. So because part of the solid are being converted to gas, so in that case you can see that there is also increase in entropy. So the first equation here, gas to liquid, there will be decrease in entropy, but in this case where we have solid breaking to give us a solid and another gas, then that shows increase in entropy. Now let's look at this formation of ammonia. The entropy is decreasing. If you look at it, gaseous, and then what do we have here? Gaseous. So if you come to look at it, which theory applies here from the four discussed earlier? If you look at this one, this is where I told you that when the number of molecules of the product is higher than the number of molecules of the reactant, there is increase in entropy. But if the number of molecules of the product is lower than the number of molecules of the reactant, then what you have is decrease in entropy. So when you look at the formation of ammonia, for instance, if you look at the reactant side, what we have there is four total reactant molecules. But when you look at the product side, you have how many? You have just two. Here nitrogen is 1 and then plus 3 hydrogen, giving us 4. But coming to where we have the ammonia, we have only just 2. So that shows a kind of decrease in entropy. Now let's look at this one. Aqueous, and then giving us another aqueous and then solid. If we look at this, there is decrease. Why? Because they said the entropy is decreasing because a solid is formed from aqueous reactant. When the reactant is in aqueous form, there is still a little bit of disorder. But by the time it's now forming a kind of a solid, there will be another, and then that shows decrease in entropy. Then here is another one, the combination of hydrogen gas and chlorine gas to form a hydrogen chloride. Then here everything is in gaseous state, and then if you look at the number of molecules too, we have 2 at the reactant side, we also have 2 at the product side. Then that means since it is equal, then entropy here is 0. There will be no decrease and there will be no increase in entropy. Okay, let's look at standard entropy. All molecular motion ceases at absolute 0. Therefore, the entropy of a pure crystalline substance at absolute 0 is defined to be equal to 0. As the temperature of substance increases, its entropy increases because of an increase in molecular motion. The absolute or standard entropy of a system can be measured. Now, the symbol for entropy is X, and the standard entropy of a system is given by the symbol S degree, indicating that the standard entropy is determined under standard condition. Then the unit for entropy, the unit of entropy is Joule per Kelvin per mole. Joule per Kelvin per mole. Standard entropy for a food substances are shown in the table in the next slide. But before that, I've told you, if you are increasing the temperature of any system, indirectly what you are doing is you are also increasing the entropy. So if the temperature of a system is at 0, then definitely the entropy of such system is also 0. Now let's look at the entropy of some all these values. You don't need to disturb yourself about it in any question you will be given, but Just look at some of it. The hydrogen gas here, we have it to be 131 per joule per Kelvin per mole. The same thing applicable. Oxygen, we have 205. Water, we have 69.9. Steam, we have 188.7. Then graphite, we have 5.69. Diamond, we have 2.4. Now, the knowledge of the absolute entropy of substances allow us to calculate the entropy change. So just as we can calculate enthalpy change, so also entropy change can be calculated. So for example, the entropy change for the vaporization of water can be found as, it will also be that of the entropy change of product minus the entropy change of reactant, just as you have in enthalpy. So if your answer is negative, then you should know entropy is decreasing, and if your answer is positive, then the entropy is increasing. So if you look at this here, for the conversion of water to liquid, let's go back to this table. If you look at this table here, for the gas, it's going to be, we are converting, for the gas here, the reaction is condensation reaction. So that means H2O gas will be our reactant, while H2O liquid, water, will be our product. So if you follow the formula, which is the entropy of product minus the entropy of reactant. So in this case, you can see we have 188.7 minus 69.9, and here we have 118.8 joule per mole. So the entropy change of the vaporization of water is positive because the gas state has higher entropy than the liquid state. So in general, the entropy change for a reaction can be determined if the standard entropy of each substance are known. Now this is the formula I told you. Here we have the total entropy of product, that's summation, and minus the total entropy of reactant, or let's just call it summation of entropy of product minus the summation of entropy of reactant will give us the change in entropy. Now, the standard entropy change is equal to the sum of all the standard entropy of the product minus the sum of all the standard entropy of the reactant. We are still talking about the previous formula in the last slide. So the symbol small n signifies that each entropy must first be multiplied by its coefficient in the balanced equation. The entropy change for the formation of liquid water from gaseous, hydrogen and oxygen can be calculated using this equation. Now let's look at this. We said the coefficient must be multiplied with their entropy. So for instance, if we have this reaction, hydrogen plus oxygen, to give us water. So here our reactant will be hydrogen and oxygen. So we are going to add the entropy of hydrogen with that of oxygen to get the total entropy for the reactant, and then we are going to subtract it from the entropy of water. But remember, we have to multiply with the coefficient. So if you go back to the table, our previous table there, you discover that for water we have the entropy to be 69.9. So we multiply the 69.9 here by 2, then minus the addition of entropy of hydrogen and then entropy of oxygen. So the first one here is for hydrogen. Hydrogen in that table is 131. So we have to multiply by the coefficient, which is 2. Oxygen there is 205. So the coefficient of oxygen here is 1. So the addition of the two, you subtract it,